Thanks everybody for joining us today for the joint CGD CISL seminar here in person and online. We're pleased to have Dr. Christopher Kadow, who's the head of the Data Analysis Department at the Organization for German Climate Computing Center. And today, Chris will be talking a little bit of background on Freva, the science gateway for the Earth systems community, from data analysis to AI/ML. So thanks again for joining us, Chris.
Yeah, thanks, Doug, thanks. I usually start with something like, I show you where you are right now, right? So we are in the US, in Colorado, in Boulder. I'm from Europe, originally from Berlin, but right now I'm living in the wonderful city of Hamburg. Pretty lovely there. And I read that the German ancestry listed as largest in Colorado is 20% who has German background. Some, great. Okay, so my next question will be harder. So who actually speaks German? Oh, some, very good, very good. So, but yeah, something happened in between, right? So these statistics doesn't match up, right? So I don't know, right? It's the most beautiful language in the world, as you know. And you could have that great accent, right? So I probably hear that. Of course, everybody thinks about the hamburger when they're in America. But as you probably know from the name Hamburg, the city where I am, it's actually from there, right? But true story is that the cheeseburger was first mentioned in Colorado. So it's that's coming from here, actually. When I tell my friends I'm going to Boulder, they think about this, right? This kind of climbing on the wall thingy. So this is actually also from here. That is kind of interesting. And then people on red stripes on the streets partying is, of course, Mardi Gras in Germany, right? So this is kind of the time of the year where kind of everybody now kind of starts to dress up. Streets are filled with people. And then the kids put on really German traditional costumes on, right? Like my niece and my nephews. So actually, that's true. So first, the most important thing is that we throw candy. So I will not do that, right? I will not throw candy now. But I brought a lot of German candy with me, so clear it out, right? So just give it around and yeah, take some. And they actually are on trucks usually, and they throw this candy into the mass of people standing there and partying. Yeah, and then the kids actually dress up very traditional German Carnival or Mardi Gras costumes. So my niece usually is a cowgirl, my other nephew is Spider-Man, and then there's also a Jedi. Yes, okay, so much for the clash of culture. As Doug said, I'm from the German Climate Computing Center. We are basically providing the German climate research community some compute, some storage, some support on several things. As I'm invited by CISL, it will be a little bit technical today, but I try to keep it colorful as much as I can. Very important partnerships, maybe you know from your research experience, are actually our shareholders, the Max Planck Institute for Meteorology, the Alfred Wegener Institute for Polar Marine Research, University of Hamburg, and the Helmholtz Center for Coastal Research. On the right, you see our beautiful building in Hamburg. That's actually pretty cool. And then on the bottom right, you see our HPC, so-called Levante, named after wind in France, actually. Okay, so nothing goes without a great team, right? So this is the data analysis department. We're actually quite still new, right? So we are we're born in 2023. And we have a cool team, kind of mixture of scientific software engineers and AI experts. And this is kind of on the right side, you see basically how the DKRZ is kind of built. We have a department on data management, one of system, which take care of the HPC. We have the scientific computing group, the applications group, and then the data analysis side, which is focusing basically on everything which happens after the Earth system modeling is done. Yes, so what I want to talk about today is, after giving you the introduction to the German Climate Computing Center, is, as Doug said already, Freva, our kind of data analysis platform, kind of an evaluation and data framework to increase efficiency for research. Then I basically just spoiler a little bit of AI stuff we're doing. I'm not going to talk about, but it's also part of our department. And then I will tell the story how these two things actually go together, right? So what I think is the future of data analysis. Okay, so maybe as a scientist, you know, then sometimes you want to do something with data. You have petabytes of data on your HPC, and you want to do something. Then a colleague says, "Yeah, I check here out. I have this notebook that does something. Oh no, I promised something. I don't know what software was actually used. So now it gets quite messy, sharing software, sharing data, and so on." And this is basically the reason why we built Freva. So it's an evaluation system framework for the Earth system science community, which brings together data and tools with the advantage of being easy accessible and also scientific reproducible, right? So the important things for our community. And what is really nice about this framework, it's quite customizable. So not every project needs all of the data sets. Not every project needs all of the software environments. So you can always kind of bring in the style of the project you want to have. So you see on the right a couple of versions actually of that Freva framework. And this is what I want to show today. So let's have a look at accessibility and basically our centralized and flexible access. So Freva is mainly a Python 3 framework, and it's running at the DKRZ HPC. It comes in 3 flavors. So it comes with the command line interface, so everybody who works in Bash, but you have also a nice web GUI where I will show the most of the things of today. But you can also use it in a Python module, therefore you can load it into your Jupyter notebook. And they are all connected, and this is actually quite nice. So they usually work all together. So if you're, for example, checking out the GUI, but let's say you start the Freva program here in the shell, and then you check your Jupyter notebook, and it's all there, then let's start kind of a run here on the Bash, which is kind of executed directly. It's so-called animator, just makes a nice movie. In the same time, you can check for certain data sets in your Jupyter notebook, which you just use for your animator thingy. And then you can go to the GUI and just click, for example, on history, and then you see that your run is already submitted, it's running. Let's check back what's doing, or it's doing the animation at the moment. So then we can jump into this, then we can check the configuration, and we can wait for the results. Here's the command we just used to kind of start this whole process. Yeah, I will talk about the Git stuff later on, and then you can just wait basically for the result to come. And here we go, and then you can have a look at the result. Good. So doing something like this, you need data, right? So the whole idea is here that we have a centralized and standardized data. So we basically follow the idea of CMOR, so stuff the ESGF, for example, is using. So you have certain facets and directory structures, but you don't have to use it, right? So we're quite flexible in adding other stuff. We have a lot of pseudo CMIP data on board. We have customized standards there, and we can all bring it together. So the data, which is kind of, let me just click on it. So the data is ingested via Solar Apache. So kind of we have a big server kind of using all these things. So we have 10 million of files, for example, in that system here right now. That's basically 4.5 petabyte of data. You can kind of use that GUI to find data. It has a lot of on-mouse over features where you can check for certain things. So it's kind of also uses some intuitive queries and therefore kind of bringing in fast results. For example, when we go now to the variable in a second, you don't have to know the variable name. You can just look for precipitation. It brings you basically the variable PR, and then you can do these things. So it has a metadata pre-visualization, it has a time selection with it. Everything is in URL. We have the indexation of POSIX data, stack or intake. If you have no clue what this is, that's fine. As I said, it's a little bit for the CISL group here, kind of where the technical background lies. And we have our S3 cloud connected to it. We have NetCDF data, grip data, ZAR data on board. Everything is basically inside of that thingy here. Okay. Here we go. That was the metadata, and it's not so important. Okay, so just to give you, how do I get back? Okay, I just want to quickly show this video as well, because finding data in a GUI is always pretty nice, but this is actually also pretty cool in the shell. So you can use actually the same data browser in the shell, but just tapping through the facets. So here right now we're looking for reanalysis data, and we want to know which reanalysis data we have at the DKRZ. We check in experiment, we do a double tap, and then it pumps out like error 5, error 20C, NCEP, and so on and so on. So this is pretty convenient to use next to the GUI, actually, if you, for example, build scripts and so on. Okay, so let me go to the incorporation of tools, right? Because this is an analysis platform. So the whole idea is that we don't force the scientists to use a certain language, programming language, right? I would love to do that, right? Everyone use Python, right? Just do it, right? That doesn't work, right? And we had to learn that pretty early on. I'm a scientist myself. You get scripts, you have stuff in R, you have stuff, I don't know, still lying around in NCL, you have a bunch of shell scripts lying around, and we say like, okay, all good, just make it work, that's all good. We usually use just non-commercial software, but if you want to use it, for example, you can do that. Then we have a standardized API around, so we have a wrapper, which basically puts the shell script here on the bottom, kind of wraps it up into a Python wrapper. And if you even don't want to use a Python wrapper, you can use a TOML wrapper, which is even more easier than that. Then you cannot hack the system anymore, but it's much easier to kind of play with it. And then in the end, it gets basically a Freva command, which is doing the same thing, but kind of translated to this thing. And then you have all the different programming language in one way of using, right? Makes the life for the users and the scientists much, much easier. That is basically the idea behind that. And with this, as I said, we have still stuff in NCL going on. Here's a movie plotter. We have stuff in R for some, here's some temperature analysis and some precip analysis here in Python. And actually, we have like much more tools in there, right? So it's more than 50 right now, but it's not really about the amount of tools, right? There are better systems out there where you can put something in and it gets maintained, right? Like the ESMBal tool suite. This is more a developer suite, kind of bring something in, change it, use it, and make it good, and then you can grab it and make it operational. But it's not about like, okay, let's get 1,000 tools in here. This is basically our GUI for the whole plugin suite. So you have tags you can set, you have like categories you can set. This is usually pretty nice. Let's have a look into the reproducibility and transparency idea. So yes, that works. That's very good. So for example, here's an example of like how this looks. So every configuration is stored and findable in a MariaDB. So you can look into the results, right? Here we have a storm over Germany, which was a pretty drastic disaster, actually. You have the configuration with it. You can check these configuration. You can even kind of modify these configurations. So you can click on Edit Configuration and change it slightly. For example, adding an extra day or something like that. And then you can rerun this whole thing, right? So, and everything is already set in that way. You don't need to do actually a lot. So we don't do that now. We actually go up again. And then when you go into the configuration, not just the Freva command, which you find here, kind of is there, which you can copy and put it into the shell, but also kind of it's connected to GitLab or GitHub or wherever the code is, and it stores the tool internal version number from the system and the plugin. So you can always set back the software to make sure this is still reproducible, and in that sense, when something changed, like the data or something like that, then you can actually share these results with your colleagues, right? So here we write to the colleague Felix that this is a great result. We submit it, and then this pops up now on the right bottom. He actually gets an email with a link to the result. He can check that result. You can work together. So the whole idea is to connecting the scientists on that way, right? So and everything can be also commented. You have kind of a comment function in there, and then we have also the result browser where you can go in and every person actually in the project can see all the results of everybody. And this way we can find results of others and I say, oh, that's also my scientific topic. Let's talk about this, let's connect and so on. Freva also suggests when you want to do something, it suggests actually results which already done with your configuration. And you can just click there and go there. You don't need to run them, right? Which also then saves CPU time, I/O, storage, it connects the scientists, so that's the whole idea. Okay. This is basically the Freva framework in a nutshell, right? This is usually the stuff I show to people to kind of advertise it a little bit. So and usually the scientific crowd is like, oh, something like this would be actually quite useful. Would be great to have something like these data thingies, software thingies, and so on. But this is basically the target audience, kind of the scientific users, right? And right now, I also want to tackle a little bit the scientific developer and the administrator, right? So it's kind of, I want to show kind of CISL a little bit what is in the background. So because this is, of course, just a glimpse of what is possible with that framework. We have much more to it, right? And I just want to focus here a little bit on 4 things just to show what is also possible. So this is also a developer platform here. Let me just click on it. Yes, that works. So for example, if you're in a GUI and you have this official plugin, Climpact SCI, doing some climate extremes, and you change something, added a variable or something like that, you can override it. And then you can use the GUI to run your own kind of plugin advancement over the existing plugin. But you can also kind of build a new plugin in the background before you make it official for everybody, and can put this into the system and test it yourself in that way that you make sure that this works. So you've plugged in this tool. So it should make life of the developers also much easier in that sense, right? So it's kind of the official platform, but also the developer platform on the side. Then we have little things, right, which are actually quite cool. We have, for example, a special function inside of the wrapper of the Freva analysis setup, basically, where you can say, okay, link the output of the certain plugin to the database. And then kind of on top, you see that function. And then you run, for example, a plugin which uses, I don't know, 5 variables and makes it 1. Right, some heat indice or something like that, and you run that, and then it ends up in the user base. You see that here on the project user thingy, so it lands directly there, and then we can use it in the next plugin to do an analysis with it. Right, so everything is basically interconnected in that way that you can put in basically the output of a plugin into the data browser again, which can be shared with everybody. And then we can make it also official and put it into a certain project also. And so this is actually quite unique. Plugin chain goes a little bit further than the usual setups of software tools. Then we have tons of documentation, right? So just to make sure everything works, we have this for developers, we have this for administrators, also of course for users, and I will not bore you with that. So for the administrative part, right? So if you think, okay, so how heavy is that system to install it? It's actually not much, right? So first thing, it's open source. It's on GitHub. It's basically an open development, so you can have a look at it. Everything is prepared with container solutions. So you just throw in your Podman or Docker container environment, and you can launch this whole system. And you can have, like you see that on the right, so one service, one machine set up, so you can put the Solar server, so the data management or the results, the MariaDB, each on one virtual machine, or you can also say, okay, we put all the services on one machine, so you're quite flexible in setting up this whole thing. And I just asked actually my team to give me this table here, what they think is a minimum requirement and a recommended environment. And they say like, yeah, minimum 4, better 6 to 8 CPUs. RAM would be 4, would be totally fine. I know people also running this on the laptops, but RAM, of course, 6 to 16 gigs would be quite good. And disk space for this raw system, 20 to 50 would be quite enough, right? Not much, actually, right? So if you have a virtual machine there, it's actually not much to set it up. That's actually quite convenient. Yes. What comes with it also for the administrators is that you get an idea of what are the people actually using, what are using for software, which plugins are run, and also for the data search, right? Do you guys know which data is actually searched at your Anchor machine, right? So if you have kind of this little loophole everybody has to go through, you can monitor which data set is needed. And when you know which data set is needed, you can also think about, maybe this is not needed, put it to tape, and put the stuff which is often used, let's keep it on kind of the fast disks, right? This is actually quite neat to have next to what the users gonna gain from it. And then we are working pretty hard right now to kind of update everything. So we already have the Freva REST API, where you can basically use that in whatever language you want to kind of use. We have the Freva client already ready, so this is also quite nice. So we're separating right now server and client infrastructure. We have the data streaming, it's close to be ready, that you can basically make an HTTP call and stream that data via the internet. And we want to connect this from file system to cloud and tape so that the users can see everything, can get everything, but they don't have to care where it's actually coming from. Because scientists usually don't care if it's on tape or if it's on cloud or if it's on somewhere in a home directory, right? So they just, okay, I want the data, I want this and this data, and they don't care where it's coming from. Then the Freva features, if we have time later and you have questions about this, is actually quite cool. We can even put in our data sets into the storage, which doesn't exist yet, which is basically produced by a plugin, and we can register it already as data, but we store it basically just as a recipe where we put in the software in place and then run the software to produce that data when it's needed, right? With this, you can also store tons of storage, right? Because you just produce it on the fly. If you have more CPU than storage, that's maybe an option. And then we're working on kind of improvements on the workflows here that we can get plugins connected to each other and so on and so on. Yeah, that was basically already the really hard technical stuff, right? So if you have questions later on, I know I meet CISL colleagues kind of in the next days, kind of about details in the background, so please let me know, right? So it's not really magic, we just connected the dots and made it quite convenient to set it up and use it. Okay, does this help for AI and ML? Actually, it is, right? So you see the Freva framework here on the left. Kind of we use this in many publications already to just think of if you want to do some machine learning stuff, you always need to have labeled data. Just imagine you have 10 million of files which are basically labeled. Right? This makes everything easier. You don't have to kind of make sure this is kind of working together because this is kind of in the background already working. So we did this reconstruction idea where we went to the past and infilled kind of old, back in the days, climate information, weather measurements, and we kind of reconstructed it. That worked quite well. Then we went to now broken radars. So you have a weather radar, precip is coming, radars are broken. Can we fill it in with AI? Actually, we can. Then we went even further, checked, okay, we have just the stations, but we want to have the full field. Does that work? It also worked. We use it for data assimilation, this case here in the ocean. We built with our colleague, Paul Kuchera, we built a digital twin of, so basically a virtual weather station, which is usually built via 3D printing. But not always these stations are very reliable. So we can just infill these moments where the data is missing by adding an AI level layer on top, which worked actually quite nice, and we're still working on that. And we did also some downscaling stuff, stuff everybody does right now. But just imagine having a tool set like Freva in the background where you can, okay, I need this and this data, I need to have observations, I need to have reanalysis data, I need to have a system model data, and just having an idea of where to get it, is it labeled, and can I use it right away for my machine learning algorithms? And that's basically what I want to show with the AI stuff. That's kind of where the basically downstream AI climate science basically stops. But this kind of whole addition of machine learning with maybe something like Freva on top, bringing it maybe to the future of data analysis, right? So, and this is where we're kind of these two sides of our department basically come together. And this is what I want to show next. So let's go to the past of the data analysis, right? In the past, there was some old professor, and he wanted to know where on Earth was the highest wind speed and when. And of course, he has no clue how to get there because he's standing in front of a microscope, right? So in the background, he has something on the wall, and he thinks and has no clue. So what does he do? He actually asks his young PhD student, who's really good in programming, and to get the job done. And she said, yeah, sure. Again, let's do it. Let's find the data, let's analyze it, and let's plot it, right? So, and then the question gets answered. So, and she said like, yeah, okay, let's go for it. I grab here wind data from era 5 between 1940 and 2023. And now let's load that data set and have a look at it. And then we go from there. And she basically writes a little Python script which does the data loading. Here we go, it's net CDF data, 65 megabyte, couple of months, 2 degree data. Now let's build a little script which kind of checks for the maximum wind speed, the location, the year, and then kind of add up kind of to put it into a plot to have a look at it. And then this thing runs, and I say, yeah, 1942, and all these years, and it's actually in Antarctica. You see that there, and so on. And then after she done that, right? So basically going through the whole traditional approach of writing some get the data, analyze it, get the maximum, doing a plot, and so on, and then gets the plot, and then gets it back to the professor. That kind of would be the old way of doing it. And you probably already recognized, right? This was not her. So we connected a large language model approach with the Freva system I showed before. Just imagine what you can do with that, right? So we built now kind of a system, a Freva GPT, on top of everything I showed you before, where you can jump into this thing, putting in a normal language question, like make a zonal mean plot of 2 climatologies, like 61 to 90 and 91 to 2020. This calls the data browser on the fly, right? You don't have to care about where's the data coming from, because that's everything basically already done. Then it does the whole setup of running it. So where's the difference between these 2 climatologies? Who knows? Precipitation. Where's the biggest one? Okay, no, not many climate scientists here on board. I see that. It's actually in the tropics. And gets the whole thingy analyzed for you, and we cut out the whole programming part, right? Coming from a normal language question to the scientific result. And now we could go on here and kind of say, oh, where's the maximum difference? Okay, which years were actually the biggest shifts? Do we see a trend in there, and so on? So we could go on and on and on, having everything in the background. And then maybe you think, right, I'm already putting in some questions you probably have in your mind. Yeah, but an LLM is doing some hallucinations, right? So isn't that a problem? Yes And no, right? Because what we're doing here is actually, we didn't train an LLM to guess the zonal means. You could try to do that, which is kind of stupid, but you could try to do that. What we do is kind of hallucinate the code, not the results. Then we execute the code, we can look at the code, we can rerun it and make sure it actually works. So, and that just to show you that it actually is hallucinating or kind of adjusting its probabilities, right? So it usually hallucinates the colors, right? So you see two different styles here of words and so on, but the result is again the same. And that's also the unique thing about this whole approach, because you can do the science, make it reproducible. Of course, it's a little bit slower because we have to do the analysis, right? But therefore, it's scientifically correct. And then you maybe ask, okay, Chris, this is nice to have these easy language thingy and does the whole programming thing and I get a result, but I'm a good programmer, right? I just need help in doing my stuff, right? Is that possible? And say, yes, because you can use that thing also as a co-pilot, right? So whoever used GitHub Copilot already. So we connected it to the Jupyter Hub, and let's assume you are here in a Jupyter Hub. You see on the left the whole, let's give me the highest wind speed here over Antarctica, in this case for 2010. This is basically the approach I showed you already. And now I'm asking for a function, right? Because I want to make something operational. I want to have a function which kind of always shows me the highest wind speed on this thing, and then kind of creates this function, which I can use then to kind of produce, for example, a tool for everybody, for someone else, right? So I can use now this function and kind of give it a certain region, and it's still Antarctica, the highest wind speed, but let's zoom into the Indian Ocean, and then it's a different region with the highest wind speed. And then I can also say, okay, explain this whole cell to me, and kind of explain this whole way of programming to me, because I have no clue. I got this function from a colleague. Right? And even more cool is actually the next thing, where let's assume you still write your own code, right? So, and on the right side, you have that code and you kind of want to run it, and then what usually happens is it gets a mistake, right? So something is wrong. So what you can do is here, using Freva GPT, and say, okay, fix this whole thing. So it loads that cell in, and gives me a corrected cell. So somebody made a typo on the word reanalysis, kind of, and then I say, okay, put this cell under the other cell. Then I can push, okay, run it again. It runs, and I'm getting the plot for the Valencia catastrophe of precipitation last year. So again, helping the users, having the scientific developers, right? Having everything connected in between. That's actually quite cool. And this kind of already kind of brings the connection between these two worlds actually quite nice. So the whole idea is that we have a context-driven analysis without barriers, right? If you can use normal words, I think everybody can do that. We're bridging the language to code gap with that, right? We are facilitating this whole data integration. So when we have a database which is already there with Freva, which is always up to date, you don't have to retrain your model always on the new data which comes in, because we're using basically the software facilities we already have at the HPC. That makes it quite fast. We are connecting a lot of interdisciplinary research with it, right? Just think about it. I have usually troubles explaining my research to other researchers, right? Just imagine talking to a biological person or physicist or something like that. Also, of course, this is quite scalable in that sense that we kind of make it small, everybody can use it, make it bigger if it needs more complexity. Still having in mind the whole idea of transparency and reproducibility, right? That's kind of the nice thing with that tool, to have like the chance to always look at the code, rerun the code, and share the code. Yes. We started actually with having everything in the GPT store, right? So everybody who uses ChatGPT, you can basically put in little tools in there that work quite nice. Then we used the API of as a GPT assistant. Both was pretty limited in that sense. It was nice and cool to see, but it was quite limited. And then kind of we put it on the HPC, having the whole analysis thing running on the HPC, made it much faster, and we have it right now running with basically all the OpenAI AI tools like GPT-4o. We have O3 Mini already on board. Whatever we want, we can actually use. And we have already Gwen, DeepSeek, and I think Llama on board. But they all speak different languages on this tool call to actually make this happen. And it was quite interesting to see with DeepSeek that it was coming out, and they basically said, oh, we forgot to put this in, wait for the next version that you can use that too. But it's basically already prepared. If you want to test it, right, I'm always brave with bringing this with me, right? So if you want to play with that tool and just want to see what's possible, if you want to use that at OpenAI, this is kind of the small version, the test version. And this is kind of what I showed you earlier is already running at DKRZ at full scale. Yeah, and this kind of whole thing, why is that maybe important, right? So you maybe heard about this whole idea of these Earth virtualization engines. Basically, the whole community, including NCAR, is pushing for global kilometer scale Earth system models. And the question is like, how the heck do we analyze that if we have these results? If we are still able to store it somewhere, and then we need to analyze these things, right, on, I don't know, minute and kilometer scale, how the heck should that work? And this is basically where everybody tries right now to push forward with certain ideas. And you see the plot. So on the left side is a little bit kind of the whole climate modeling or the Earth system modeling. And on the right, it should be an easy interface to talk to. Yeah, I think you make the connection yourself, right? So that would be kind of one way of doing it. But we need to have the best high-performance computers in the world to actually do that, to simulate and store and analyze these things. But still, it should be convenient to do that, right? Because it's actually not us doing that, but the impact modelers, right? The society, industry, economy. They will want to know what's happening actually in 1 year in my specific district and so on and so on. And the first activity started already, right? So there's this huge global kilometer scale hackathon, and it's also happening here at NCAR, actually. You can kind of check the websites and log in, and if you want to have a hands-on on these first kilometer scale models to do some analysis with it, I'm happy to advertise that here. Okay, and kind of before I sum up, I also want to get one question out of the way, because people always, when I talk about these things, want to talk, but either this thing will destroy us or at least cost our jobs, right? So, what I think will happen with these two in the future, I think we have much more time to do science, right? Why the heck do scientists actually need to program? That question you can actually ask, right? Why is that necessary? Because we needed to do it to kind of get the data and the information out of the data and so on, right? So, but if we are capable of making this tool or these kind of tools really performant, then I think we can accelerate our science, right? We would be on a much faster pace to do science. We have to do less programming. We could do these things, right? So, I mean, nobody would take away the calculator anymore, right? So just always keep that in mind. Why the heck do I have to understand how a car works to use a car, right? Of course, there are people who want to understand how a car works. Fair enough, I don't, right? And then for the professor, actually, I think this is the real revolution that takes place. The senior scientist revolution, that is the thing that will happen, because he will be basically freed from the chains of programming, right? So he has all that knowledge, that experience. And just imagine he has such a tool. We can use normal language to do his science or her science, right? So, and it's pretty funny how the AI made these pictures, right? So kind of, it's all thing about glasses, I think, right? So it kind of, for the female young scientist, it's kind of getting rid of the glasses. And for the old professor, it's kind of getting these evil mind glasses to be a villain, right? So, yeah. But we can discuss about this, of course, right? So, okay, let me sum up before we come into the questions. So what I wanted to show you today is kind of introducing the German Climate Computing Center, where I'm the head of the data analysis department. The whole idea is to bringing these two worlds, climate science, earth system science, next to informatics, using these new methods and architectures on my HPC as easy as possible for the whole community, right? And then I showed you the evaluation and data platform to kind of do analysis, to do kind of data search, kind of connecting the scientists, making sure everything is traceable, reusable, and so on. And it still hides the complexity of an HPC environment here, right? That everybody can already concentrate a little bit more on research than they usually are when they're kind of fighting through all these scripts. And then I just kind of really fast showed that we're also doing a lot of cool AI stuff and building a lot of software around that. So we're having super resolution there, broken weather radars, storms, extreme events, virtual weather stations, data assimilation, and so on. We're using this with modern technologies, but doing classical research, which is actually quite nice and a lot of fun as well. I can bring that with me also on another day again. And then I kind of showed you what I think is the next step for the data analysis in our community, adding basically the whole idea of large language models on top of such a machinery, which is something like Freva, to make it even more easy to bringing basically normal language analysis into the game, still being scientifically correct, at least traceable, and kind of cutting the whole programming part a little bit, or at least reducing it like a lot. And with that, I thank you for your attention. I'm happy to answer some questions.
Okay, so any questions for Chris? Goodness, they have the ceiling mics on. So.
Yeah, this was really cool. Thank you. I've got a bunch of questions, so I'm going to follow up with you on email later. My two simple questions for now, hopefully simple. How many concurrent users do you guys have at the moment? And does it scale when you're trying to analyze data with that?
Yeah, so you're talking about basically about the classical, right? So
yes.
Yeah, so the nice thing is that so we have usually like four research projects at the same time, where we have usually like, I would say like usually like 100 users, but it would be more like 40 to 50 hardcore users, and they are doing, let's say, like 30 analysis per day or something like that. So it's pretty medium, but altogether it comes together. But we are quite flexible in ramping it up, because the whole analysis behind Freva is actually done on a HPC. So we are basically pumping the analysis scripts into Slurm, right, the scheduler.
Sure. And
this is kind of scaling by itself, because the modeling community needs this anyway, and we are hooking in, and that therefore we can extend that due to the amount of compute resources we have.
Yeah, thanks. I'll let other people ask something before I continue.
We have a question online from Megan. She said, great presentation, thanks for sharing. Could you please discuss the data limitations on Freva GPT? For example, there is a 20-file limit for custom GPTs on ChatGPT, regardless of whether the data is structured or unstructured, and there are size restrictions as well. Do you have a version outside?
Yes. So exactly. So we started actually on this, and then it's quite limited, right? So that was the stuff I showed earlier. So let me just quickly jump to that slide again. Is that, it's not, that's also fine. So, yeah, thank you very much. So kind of the two first stages, that's basically what you're talking about. And we are right now on the DKRZ, calling the API, in that case from OpenAI in stage 3, and we are doing the whole analysis and all the data mumbo jumbo we're doing on our HPC, local. Therefore, we have a lot of power, right? So we have big machines, we have a lot of analysis to hardware around, and we can actually do that. We're just using the LLM to kind of set up the scripts we run at the DKRZ. And therefore, we are not limited anymore by whatever the GPT store or other service providers like Gemini and so on are offering. We are doing this at our HPC. And next step would be even going further, cutting out the OpenAI LLMs, right, and going totally local with our own and hopefully open source LLM to make sure everything is run at our HPC. DeepSeek, Gwen, Llama, they're still okay-ish, let's say, put it mildly. But I have high hopes that this is actually the year of the open source community, at least to connect. I hope that helps, Megan.
Yeah, go ahead.
I was wondering how you think this tool could project onto community code development efforts. In particular, I guess if you have people interacting with the machine, are you training on those interactions, or does code that ends up getting used enter some kind of database? And is there a place, so you've emphasized the traceability of the code. Is there a place for some kind of like testing or validation that this is actually giving you something, demonstrably what you would like?
Oh yeah, that's a very, very good point. Thanks for bringing it up. So we basically saving all the analysis, not just the analysis tools, but all the analysis itself we're storing in a MariaDB. So we have a database where all the analysis is done in there, and we can train on that, right? So on the successful ones, right? But also it kind of allows every user to kind of check which analysis was done before, right? And to, what was the last point? Sorry. So we are...
Kind of like verification, correctness of
Yeah,
software.
exactly. So, and we usually don't, right, so you've seen the spectrum of people we try to get, right? We have these simple users who just want to click on the GUI, and then we have these scientific programmers who say like, oh, I want to do this, everything I want, give me a shell version or something like this. And this is usually a wide spectrum of people we want to tackle, and that therefore we don't say, please write tests, but we have a continuous integration facility around Freva. And every time we update something, we can run actually all these tools and say, okay, make sure this scientific test actually works and so on. Yeah, so this is a little bit in these administration machinery behind this thing, which is kind of shielded usually from the users because they really don't care. The scientific programmers usually say, okay, if I write this tool and I use Git, I'm already doing a lot. And we say, yeah, okay, fine. But if there are people like, oh, should we do tests to make sure this is actually scientific valid? Then we say, yeah, great. Here we go. Here's CICD. We help you to set up these things. And then you can actually test these things on the fly, making sure these tools are working, even if things are updated, right? And most of the time, it's actually not us updating stuff, but if Python 3 gets into the next version or a kind of a software environment in the background is changed and so on. Yes, but we can all, so this is kind of on the classical side, and for the LLM side, we will use that database to kind of train the LLMs to making sure this thing can also help me to set up these things, right? This also makes it easier. I hope that goes in direction. Thanks.
Yep. Great. Back there.
Okay, I'm wondering about how you see this kind of fitting in with like education and like teaching students to code. Like, do we still do that if they could just type in, make this plot for me, you know?
Yeah, that's a good point. We did that last year in the climate modeling class in Hamburg. So they still did this whole, they did some energy balance modeling or something like that, and then they did get some climate data to be analyzed. And I was playing basically the bad student to kind of do everything with a bot. And I was showing them like, okay, now let's do your analysis with a bot, and where are the edges, what is possible, what not. And very often other professors come to me and say like, is that good or is that not good? Should we do that or should we not do that? And I usually say like, yeah, go for it. Just make it more complex, make it more hard, right? So if you have simple tasks where they of course need to code a simple visualization, maybe that's also not the thing they should do anymore, right? If it's that easy, right? So of course, if the whole class is about visualization, then maybe, but if it's just a tool to get to the next scientific analysis, I would say, why not using these kind of tools? But you're right, there's happening a lot on these things, right? My machine learning and climate science class in Hamburg, beginning of 2022, I stopped to let them write essays, right? because ChatGPT could do it on the fly, right? And I told them, guys, you have to do posters now. Right, so and at least give them, and I usually say like, use whatever you want with these kind of tasks. And we as the teachers, we need to adapt to that thing. So, and this is something we cannot roll back, right? And we cannot say, write your essay now with a pen in class, right? I mean, that's just so backward, right? So yeah, it's a big discussion in Hamburg right now, and I think students will change a lot. Also, what they know, it will be different in a couple of years, right? Because I still kind of put my head into climate modeling code, right? I saw Fortran code and so on. I think also our community have to adjust on the fly of what can we expect actually from people, and we have certain experts which hopefully still understand the Fortran code and certain things, right? But not everybody's doing it anymore.
Could you give me an idea of like the maturity and also the user base / adoption of this platform? Like, are other modeling centers using it? Have you gotten any major feature requests from other users other than like DKRZ?
Yeah, so we had this running on a couple of sites, but usually sometimes just for beta testing, for example, the Barcelona Supercomputing Center. We actually had a system running here at RAL for a couple of months just to set it up. Paul was quite early on and said like, oh, that's actually quite nice, but it was never used in a kind of really scientific environment. We use it in 2 universities in Germany, and the German Weather Service uses the system and actually does much more evaluations with it. So alone last year, it did 120,000 analysis with the Freva framework, right? Because they're doing the whole operational chain of seasonal and decadal predictions with it. And they have requests, yes. And we usually kind of try to adjust things. We also throw away stuff, actually, which we don't need anymore, because we see that this is, okay, it was a nice idea, but it doesn't work. And it's an open development, right? So everybody can actually go in there, put in pull requests and so on, and we are quite open in doing that. And we want to scale it up at some point, yeah. But it's also quite hard, actually, without amount of resources, right, to manage these things, but it's pretty easy. We made sure that it's quite easy to install for any site who at least want to play with it first before they scale it up.
All right, any final? We have one online?
We have 3 online.
Okay. We have time because
Okay.
we left this plenty of time.
Would you like me to read them?
Yes, I can also, yeah.
I'm
Okay.
happy to read them.
Yeah. So no, we were running it as so the first question is about the container website. So we have the web interface, right? It is online, and we can access it via a normal HTTPS request, right? So if you have a VM open to the outside world, you can use the website and directly use Freva like this. No user has to use a container, right? This is also, I know, this is sometimes confusing when I try to kind of tell everybody the whole story, right? So then the users say, oh, I have to install a container. No, you don't, right? That's why administration is for. Administration gets a container, and they usually say, okay, that makes life a little bit easier than running all these kind of configure files and so on. As a user, you don't have to do anything. In the shell, you use just module system, module load, done. And on the web, you just access the website of the project. Okay. Thanks. And then the others, we provide several scripts as a database, and then produce code. Okay. Oh, yes, sorry. Running local items makes a lot of sense compared to using it as a cost configure. Yes, I agree. So that's basically the add-on from we already had from Megan, right?
Yes.
So yeah, you're absolutely right. So yeah, you understood it correctly. So we have basically a lot of scripts kind of we put in as good examples, and to make sure kind of the bot is reacting in that sense, and we put a lot of context learning around where we say, don't talk about politics these days, right? So focus on climate data analysis, and to make sure we have good examples where the bot can actually rely on. Yeah, exactly, Megan. Okay, and then Yvonne asked, do you need to train a specific LLM to write the code for us, or use a more generic? Yes, so we use the general one, right? So we're using GPT-4o right now. What you've seen was GPT-4o. We can also use GPT-4 mini, for example. And then we have the same context learning container. This is actually what we did, right? So we basically wrote this tool where we can connect any LLM, could be OpenAI, could be local, could be connected to this thing. It uses this whole context learning environment and the tool set which can be applied locally on your HPC. And therefore, we can, whatever the next LLM is, right? And there will be the next, right? So, and we can just switch. We just call it Freva GPT, basically, right? So it's not really about the LLM itself. And we will not do an LLM training, right? I mean, this is just out of league, right? So even our HPC is not able to do that. We are experimenting soon with some fine-tuning. I'm not sure if it will be better than the context learning, but we will try to get it done. Some fine-tuning. This is also, I know, fine-tuning for modelers is usually a different word, but in that case, it's kind of putting another layer on, and we want to kind of test that. But we can basically use a generic LLM and then let the generic LLM focus on the stuff we want. Thanks, Stefan.
All right, anything else? If not, if you want to get in touch with Chris, contact me. I'm schuster@ucar.edu, and he has an agenda for the week. We can sign you up, give you the link for that. And thanks again, Chris.
You're welcome. Thanks.